Big brain ideas explained simply. Welcome to Every Week Cog Neuro. This week our topic is the opposing process theory, a theory that tells you how your brain perceives the world. I'm here in the London Covent Garden, one of the busiest places in the world. To walk around safely, we need to learn many rules from the world, like how the traffic goes and where the things usually are. The fact that I can walk through all these without getting hit shows how stable and accurate our predictions are. But sometimes prediction can fail. When I'm climbing upstairs while thinking about something else, I may step into an empty stair and trip. My brain expects one was there, but there wasn't. That sudden drop shows how strong we rely on predictions and how fast you react when it goes wrong. So how does our brain balance strong expectations with fast reaction to surprise? Let's look at two classic ideas. The Bayesian view says expectation makes perception more accurate. When the sensory income is very noisy, our brain fills the gap using the most likely guess. On the left panel, you can see the hollow face illusion. When a face is actually hollow, we still perceive it to be pointing out because we have some hardwired expectation on faces to be convex. So the Bayesian view suggests that we enhance our representation of the expected event and reduce the representation of the unexpected event so that we can have a stable and accurate perception. Cancellation view says the opposite. The expected events are reduced so we can focus on more informative information with this unexpected event. And that is why you cannot tickle yourself. Your brain can always predict your own movement and then cancels it. So we land at a paradox. How can our perception both aim for accuracy and highlight surprise, which is a more informative information? The opposing process theory came up by Professor Claire Press that both mechanisms can be true, but they just operate at different times. Before we saw something, our brain used its past experience to form some expectations on what we're going to see or feel. And this helps to prepare our sensory region in advance so we can perceive the events easier and quicker when it comes. However, when in reality, the reality disagrees with our expectation, like we fell off from the stairs, we will enhance the unexpected signal quickly so we can react and to learn. So our brain first predicts and then updates. We tested this idea in our lab using electroencephalogram, or in short EEG. In our test, participants perform finger movements when seeing an avatar hand on the screen that either do the same action or different one. People also wear EEG cap, which record their brain activity when they're looking at the avatar hand movements on the screen. After we analyzed the brain signals, we found that just before people move their fingers, the expected events are represented more vividly in their brain, which means they are trying to prepare for future events that they expect to see. However, later in time, when they realize something is different from their expectation, the unexpected signals get more vividly represented in their brain, and which means they are kind of updating their internal model in their brain. And this kind of temporal flip in our data suggests an opposing process that undergoes our perception. Overall, these two stages help us to stay both accurate and flexible, using what we know by also staying alert to the new events. And this kind of temporal balance helps us to navigating our city, to catch falling objects, but also to learn from new experiences. That's everything for this week. See you next time on Every Week Cog Neuro. Big brain ideas explained simply.